Hi there and welcome back again. So if you've ever spent some time on technical discussion forums like Stack Overflow, then you will find that the same questions come up again and again. And if you follow database related forums, for example on Stack Overflow, then you will see that a question of this kind occurs again and again. All right. So this question relates to the order of operations when you load a table and its associated index. And this discussion, for example, that discussion that's linked from this particular slide, is asking whether this sequence of operations, like create the table, of course it will be empty, okay. Don't create an index yet, then load all rows into the table. In this case, it's 5 million rows. All right, so load 5 million rows. Okay, only then create an index. Only then create an index so that you end up with a loaded table and a loaded index at this particular point below here. Okay, is this the favorable order of operations? Or would this be the favorable order of operations? Of course, create the empty table first. We have to start with that. Then create an empty index on this table. So no rows yet here. So this statement, the create index statement, will create an empty index for us. Okay, and only then load into the table. And as you know, of course, not only the table will be loaded, but also the index will be loaded at this particular point. Indexes are maintained automatically. We end up with a loaded index and a loaded table in both cases, in both orders of operations. But is there any better order, or a good or a bad order of operations? What would be the answer to this question? And well, as I already tried to indicate here, these questions and discussions can become heated. All right, so let's try to settle this here, at least in the context of our discussion here in the DB2 course. And well, let's try and see what happens in these particular insertion orders in our system. For that, let's switch back to the terminal again. We haven't been to the PostgreSQL terminal for a while in the last few videos. Now it's time to return here. That's nice. Okay, so I'm going to do just that. I will create the table. I will not create an index yet. You see, there is no primary key modifier here in these columns, so no primary key or B+Tree index will be created. Okay, so no index yet. I will then load the 5 million rows. You see the 5 million integers that I'm generating here. All of these rows will be loaded into the table, and only then I'm going to create the index. At this point, the 5 million entries, the 5 million rows of the index table will be moved and loaded into our new B+Tree index, index_A. Okay, so let's see what happens if we run this experiment. I've pre-recorded this particular experiment, again, because it's a performance critical experiment, and this system is currently loaded with video recording and decoding, and I would like to measure database performance and not OBS or video recording performance. Okay, so let's run this particular experiment. And there we go. So let's run the statements. Okay. So 10 milliseconds of table creation time. Let me disregard that. But here we've got the insertion time into the table. That's 34 seconds. You notice that I've cut the video to save you some waiting time here. So, but this is just 34 seconds for loading the table. And then 5.4 seconds, only 5.4 seconds to load all the 5 million rows into the index to create the index. And that already concludes this particular part of the experiment. So let's take a record, 34 seconds, row loading, 5.4 seconds index creation. We are just below 40 seconds for the sequence of operations. Okay, clear terminal. Now the second order of operations. In the second of operations, of course, create table first, then create empty index. All right. No rows in the table, no rows in the index. Then load 5 million rows into the table. As a side effect, also the index will be maintained and we end up with 5 million entries in the index too. All right, so time to start the second experiment. Here we go, run. All right. Okay, so that's a different picture, yeah? Okay, let's finish the experiment. All right, so table creation again in the order of milliseconds. Let's disregard that. Index creation takes almost no time. That's 1.9 milliseconds. Of course, the table is empty. The index will be empty. Probably only a root page will be allocated at this particular point in time. Nothing to see here. But then the joint loading of the table as well as the index takes about 55 seconds. So in all, we end up with a loading time of 55 seconds as compared to the less than 40 seconds in this first experiment. So it appears that the first experiment indeed wins, and that this order of the second order of operations here really is problematic in the performance sense, not in the semantic sense, in the performance sense. And what we see here is an effect. Well, we see many effects. One of the effects is that when you perform this insert statement, then of course pages of the indexed table, pages of the table that we are inserting into, and pages of the index itself have to be present in the buffer, because both are being maintained in parallel. All right, so we need space in the buffer for the table, we need space in the buffer for the index, and both are competing for space there. So we are seeing some buffer congestion effects here in this particular point. All right, but there's a different explanation why, or an additional explanation why this first order of operations, so insert into the table first, done, then load all of the 5 million entries into the index. There's a different explanation why this performed so well in this case. And to see why, let's switch back to the slides for a minute. Okay, so what actually happened here is a particularly good case for the database system. All right, so let's see how the index loading indeed was performed here. All right, so let's assume that this is the B+Tree that we have created so far. All right, and we now need to insert the next row into the index. To do that, to do this bulk index loading, so load all of the stuff from the table, all of the 5 million rows from the table, load them into the index now. Okay. While this bulk loading is performed, the database system scans the table file, the source of the rows that we need to insert into the index. It will scan the table file from left to right, and it will encounter the rows inside this heap file in insertion order, because this normal insertion inserted all the rows one after the other in the left to right order from the beginning of the file to the end of the file. This is also the scan order. We will scan the rows in this particular order to fetch them and insert them into the index. If you recall the generate series command that we've used to create this particular file or the particular table, then let's switch back there. You see that we start with the lowest key value and ended with the highest key value. And this is the insertion order and will also be the order of rows in the heap file. We can actually count on that. No other operations were happening on the heap file in the meantime between insertion and index creation. We can count on the fact that the rows in the heap file are in ascending key order. All right, so the row with the lowest key value is found here. The row with the highest key value is found at the end of the file. This is exactly the order in which we scan the file. So the next key that we are going to insert in this B+Tree will be the largest key that had ever been seen and inserted. All right. If this is the largest key, if the next key is the largest key, then the tree insert routine will start its search for the correct leaf node that should hold the next new key. It will start its search at the root node and then follow the rightmost path in the tree until it hits the rightmost leaf, where this new key, of course, has to be placed. Recall that the sequence set chain is ordered. Of course, we will hit the rightmost leaf here with the new largest key. Let's insert it there, if there is still enough room. And let's consider the next key in the file, which of course will be the largest key that we have ever seen. The next tree insert routine will lead us from the top of the tree downward the rightmost path to the rightmost leaf, and this is where we're going to insert. Maybe there is not enough space in this particular leaf, then we have to allocate a new leaf. A new separator has to be inserted into the inner index node above, all right? But that would be an inner index node that's also located on the rightmost path down the tree here. All the splits of inner nodes that may have to be performed, if we're lucky, there are not many of these splits to be performed, but all of these splits, if they happen on the rightmost path here. The hot region of the B+Tree really is the rightmost path and the rightmost leaf in the sequence set chain. That's all that's active. There's only one more other page active, and that's the currently scanned file in the heap file of the table. That's only this particular page. And that's all there is to active pages in the current situation. The rightmost path of the B+Tree will probably only hold like 2, 3, maybe 4 in really large cases of pages. And then there's this additional heap file page that is busy while we are inserting rows. And this is really easy on the buffer space, and we can really take advantage there. Further, PostgreSQL will detect that we are hitting this very favorable situation where scanning order and insertion order is just the ascending key order. It will detect this, regularity, and it will activate a hot path, a hot code path in this particular case inside the B+Tree insertion code that will lead us immediately, during an insertion, it will lead us immediately to the rightmost leaf inside the B+Tree. So we will not enter the B+Tree at its root only to follow the rightmost path anyway. We will immediately enter the B+Tree in this particular hot code path situation at the rightmost leaf here and immediately perform the insertion. So we save some tree traversal effort there and immediately enter the tree at the point where the search will lead us anyway. Okay, so this is the reason why PostgreSQL performs so well in this particular situation. Indeed, we could try and trick PostgreSQL and lead it into a trap, or at least create a less favorable situation by placing the keys inside the zip file in descending order. So not in ascending order, but in descending order. Should subvert this hot code path in PostgreSQL. It should not detect that this favorable situation is present, and we should see some slowdown there. So let's test our hypothesis that indeed this hot code path that created a nicely clustered index, that this is not activated if the underlying heap file is sorted in the wrong order, in a sense. Okay, so let's do that. Let's switch over to the terminal once more, and let's switch to that part of the experiment that makes life hard for PostgreSQL, because after we created the table, we insert the keys in descending fashion. Okay, so it's just counter the the ascending key order that we could exploit in the second experiment. The third experiment is really in so let's counter the key insertion order of the first experiment and the second experiment actually. So let's make life hard here for PostgreSQL. And let's see whether we can see some performance consequences of that. Again, I have pre-recorded this particular experiment because of its performance criticality. And there it runs. All right, so creation of the table in the descending key order, and only then the creation of the index. You can see we have observed like 34 seconds of table creation time before. That's almost the same time that we see here now. So table creation really is indifferent to the order of the keys that we are placing inside the file, but index creation isn't. If you recall, we had the index loading or index creation time of 5.4 seconds in the good case, where insertion order coincides with key order. It's different now. It's 7.6 seconds in this particular case, where we cannot exploit the hot code path inside PostgreSQL and are indeed suffering from insertion order that really mismatches the key order. All right, so this concludes our mini series of experiments on the bulk loading of the mass loading of rows into B+Trees. And it also should settle that Stack Overflow discussion once and for all. Nice. So I think we should draw a line now under our current discussion of B+Trees, and for the next 2 or 3 videos switch over to MonadDB again and see how MonadDB can benefit from the presence of ordered indexes. As we will see, B+Trees do not play a role there in MonadDB. Something else is going on. But we will return to B+Trees and their practical use in query evaluation and how we find B+Trees that particularly match the current query workload that we are trying to perform on our database system. Then B+Trees will come up and be on the table again. But for now, let's close this video. Thanks for your attention, and I hope to see you around for some MonadDB discussion in the next videos. Bye there.